Hello, everyone. Thank you for coming. My name is Bob Steagall, and this is the second talk at this year's Back to Basics track. Each session in the Back to Basics track is about a single concrete topic like this one, which is entitled The Structure of a Program. Our goal is to produce content that covers important things you need to know to be a working programmer in today's C++ community. That being said, many thanks to our Back to Basics track chair, Arthur O'Dwyer, for putting together the track program, and to our conference chair, John Cowell, for making CppCon such a great experience, and for dealing with the difficulties this year. In this talk, I plan to cover things like the process of building a program, what a translation unit is and its relationship to the code that you write, the various phases of translation, which means taking a program from source code to executable, declarations, definitions, and linkage, the one definition rule, storage duration, ABIs and name mangling, linkage and loading. My goal in this talk, my goals are threefold. First, I'd like to describe a few very important global concepts. Global in the sense that these are probably fundamental things that every serious C++ programmer should know, but don't necessarily dive too deeply into the language itself. Although certainly, like everything in C++, there probably is no bottom to the rabbit hole for some of these things. I'd like to clarify terminology that gets used a lot, and that can be confusing, especially to those of us who are perhaps less experienced or just starting with C++. Terminology that can be confusing. And I'd like to shine a little bit of light, at least at a very high level, on how C++ compilation works. It's been my experience in recent employment that some of our engineers coming out of college and those with lots of experience in other languages and not much experience in C++ seem to have some difficulty understanding what actually goes on under the hood when a C++ program is built. And this lack of understanding, I think, hampered their effectiveness in some ways. And so it's my hope that by providing this somewhat basic tutorial on these important but also kind of basic topics, that I either help fill in the gaps or maybe help improve the understanding of some of the less experienced who may be watching this. So let's talk about building and running a C++ program. Let's start at a very high level, the 50,000-foot view. We begin with input files, our C++ source code. And we take those input files and we process them through some development tool chain. If you're like me, typically this is a loop that you go through from the development tools back to the input files. It's edit, compile, over and over again, until at some point you're either smart or lucky and you get an executable file. Once you have an executable file, you want to run the program, so the OS loader takes over, and you end up with an image running in the operating system. Now, at some point, usually it ends, and you go back to the development tool chain. You fix a bug, you add a new feature, you modify operation, you take away functionality, but you have to change the program to create a new version. So an important part of this talk is talking about the input files, our C++ source code, and how they should be structured in such a way that one can create working programs. So let's talk about user-defined code. This is, in my mind, this is the code that you write. And this consists of header files, source code files, and resource files. Now, resource files are those things which contain things like icons, cursors, internationalization translations, things which you may want bound into a program when you deliver that program, but which don't contribute to the execution of the program and are not part of the actual source code that you write. And then we have our dependencies. And I think of dependencies as being effectively the libraries that we use. The libraries that we use will provide header files like std, the standard library vector, or boost text.hpp, if you want to use that facility from Boost. Libraries oftentimes provide pre-compiled files, files that have object or executable code pre-compiled, like the standard libraries from GCC, Clang, the Microsoft Runtime Library, the Microsoft WinSock Library, or CRT 1.0, which is magic object code used on Linux to make your program load and run. And oftentimes, libraries will provide source code. For some libraries, those that are not header-only, like Boost, for example, to get the library to work, not only do you have to employ the headers, but you have to download the source and build the source, and building that library source becomes part of your build process. And as I mentioned before, the idea of resources. Libraries can come with resources bound into their static archives or to their shared objects. And these resources can be icons or images or translations used for internationalization. One thing to keep in mind, and perhaps a question to ask yourself as we go through these slides, is why is there this division between header files and source files? Why do we structure things in the way that we do? And when we talk about declarations and definitions in the one definition rule, hopefully it will become apparent why there is this bifurcation in the code that we write. So let's look at the C++ ecosystem, the programming ecosystem. It's actually fairly complex, surprisingly so, especially in today's world. You have us, the programmer, and a whole wide variety of things and flows of information between those things that contribute to the executable file that we're trying to create. We have tools for managing source code, and we have tools, editors, and IDEs that are used to compose and maintain the source code itself. There's a whole wide variety of these, hundreds of editors, and probably a few tens, if not 100 or more IDEs. Then we have our version control systems like, well, Git is the one I think most people use today, which we use to manage the versions of our source code so we can keep track of changes that have occurred over time. And again, there are a large variety of these. I've just picked a few out at random, including some that I've used in the past for this little balloon. We have tools that help us manage dependencies. The big one these days seems to be Conan, but there are certainly others. There's Build2, there's Buckaroo. People do dependency management with CMake. You can do dependency management with Make itself. Visual Studio and Microsoft have NuGet and VC Package. And then, of course, you can manage packages and dependencies, libraries, yourself manually, which is kind of the old school way of doing it. We have tools that manage the actual process of the build itself. The traditional Make, Nmake, CMake. There's Ninja and Incredibuild, Jam. There's Boost Build. There's MS Build. There's a whole slew of things which automatically manage taking groups of source code files and turning them into programs for you. And let's not forget the compiler. There are all kinds of compilers, well, not all kinds, but there's certainly a good variety of compilers available these days, from Clang to GCC. There's Microsoft's compiler. We have the Intel compiler, the Portland Group compiler. We have the IBM's compiler, and there are a few more. Although writing a compiler is such a big and difficult and expensive task these days, there aren't nearly as many compilers as there are editors. And then finally, there's the linker. And there are, well, quite a bit fewer of these than there are compilers. I've just listed the names of the ones that I've used. LD, LDBFD, LD Gold, and LLD. I've used all of those on Linux. I think LD is the name that's traditionally used for the linker on other platforms, and I've worked on Solaris and Linux and FreeBSD, and they all call the linker LD. And of course, with Microsoft, there's the venerable link.exe. All of those things conspire to help build the executable file, the program you're trying to make. Now, we don't always build executables. Sometimes we build dynamically linked libraries. And the process for building that is surprisingly similar. It's almost identical to that of building an executable. The difference between a shared object and an executable in most cases is that an executable has extra code in it that allows the operating system loader to load the program into memory, begin its execution, and it contains a main function. DLLs, shared objects, typically don't have those things. But DLLs and shared objects are not the only kind of libraries we want to write. There are also static archives. On Linux, they have the extension .a. There's a tool called the archiver, and it builds a thing called a static archive, a library, which is basically just a concatenation of object code from a bunch of compiled modules. Windows has its library, and it creates static archives with the .lib extension. It's not quite as extensive as that of building a shared object or an executable because there's no need to worry about main or do fix-ups that are required by linking or relocations. So static archives are actually quite a bit simpler than shared objects or executables. So our focus in this talk is really going to be on the first three stages of that initial diagram: taking input files through a development tool chain and creating executable files. And again, I just want to be clear, this is a very high-level view intended to help people fill in their knowledge gaps with regard to these things. If you're coming to C++ from another language like Java or Python and you've never worked in a compiled environment before, I think you'll find this helpful. At least I hope you will. So how do we represent our C++ programs? I mean, our programs, the code that we write, they tell the compiler what we want the underlying hardware to do. Well, we represent our programs by source code, and source code is expressed in human-readable text files. We typically have three kinds of source code. I think I mentioned them before. We have header files, also called headers, which are generally used more than once when building an executable. We have source files, and I would just call them source, which are generally used only once when building an executable. And we have resource files used to represent special non-executable information, again, like cursors or icons, images, or internationalization translations. So from this point forward, when I say source code, I mean the totality or the set union of header files and source files in general. Likewise, the terms header files, header, source files, and source are strict subsets of that encompassing term, source code. I won't mention resource files anymore as they're not relevant to this discussion. So at the bottom is a trivial C++ program to print hello. It's slightly more complex than hello world and chosen to raise a few questions, or to raise the question, why does this work? Or how does this program build? We have the definition of the function we want to run, print hello. We have an implementation of print hello, and we have a main function that calls print hello, and when executed will actually print it to the terminal. So when we build an executable, builds are accomplished through the process of compilation and linking. Why do we do this? Well, our human-readable text files must be converted to binary machine language. And so the picture I'd like you to keep in mind is this. Let's strip out things that that are not pertinent to the discussion, having to do with the tool chains and how tool chains interact, and just look at the basics. We have our headers and our source. We have library headers and possibly library source codes. We have the process of compilation, which gives us object files. We have the process of linking, which takes the object files that we create and adds to them the object code from libraries that we want to use. And if everything works well and we've done our job, and maybe even if we're lucky, we get an executable file. So what we'll do is we'll dig into this a little bit more as we go. Let's talk about compilation. Compilation is the process of taking our source code and turning it into binary code, usually called object code files. From a compiler design, a high-level perspective, it's usually described as consisting of four parts: lexical analysis, syntax analysis, semantic analysis, and code generation. Now, lexical analysis is usually called scanning or tokenization. It happens before you do syntax analysis, and it converts the code into tokens, which are the parts of of the code that the program actually used to construct binaries. Syntax analysis, which we also call parsing, involves reading through the token sequence that comes in from the lexical analysis phase to identify the syntactic structure of the program. In this phase, we typically build something called a parse tree, which replaces the linear sequence of tokens with a tree structure that's built according to the rules of a formal grammar that describes the language. And that parse tree is analyzed and transformed by later phases in the compiler. Semantic analysis adds semantic information about the intent of the program into the parse tree, and it builds a symbol table. It does semantic checks, for example, type checking, making sure that types match correctly in expressions. It does object binding, which means associating variable and function references with their definitions. It does assignment. It rejects incorrect programs or issues warnings. And finally, the last step is code generation, which is the process in which a compiler's code generator takes the intermediate representation that comes from semantic analysis and it turns it into machine code. In C++, we typically generate one object code file for each distinct source file. Every .cpp or .cxx or .cc file typically results in one corresponding .o or .obj file, depending what platform you're working on. Linking is really the process of taking the object files that come out of the compiler, combining them with object code in our binary libraries, stitching it all together, and making a working program that we can run. Now, the standard calls the process of compilation translation. And in C++, translation is performed on something called a translation unit in 9 well-defined stages. And those 9 stages cover the 4 phases of compilation, if you will, that I just mentioned, except they lay things out perhaps in greater detail. The committee has very evocatively named these phases 1 through 9. So I mentioned translation unit. What is that? Well, translation unit is defined roughly. This is not an exact definition. It's defined roughly as a source file plus all of the headers and source files that are included in it via the include preprocessing directive, minus any source code lines that are skipped by conditional directives. For example, if you've if-def in or if-def out a section of code, and with all macros expanded. So here's a simple graphical representation of the 9 phases of translation. And I'm going to briefly touch on each one of the 9 because I think they're important to understand. So in phase 1, individual bytes of the source file are mapped into characters of something that's called the basic source character set. And the basic source character set consists of 96 characters. The space character, 4 non-printing control characters like tab and new line, and 91 graphical characters, the 91 characters that you see when you type code into a C++ program. In phase 2, lines that are escaped with a backslash character at the end of the line are concatenated. Every instance of a backslash character that's immediately followed by a new line character is deleted, and the physical source code lines are spliced together to make a new logical source code line. In phase 3, the source file is decomposed into something called pre-processing tokens and sequences of white space characters and comments. Now, a pre-processing token is the minimal lexical element of the language that's necessary for phases 3 through 6, defined by the standard. There are several categories of pre-processing token, and the set of pre-processing tokens is actually a superset of the set of tokens that's recognized by the compiler itself. There are header names, there are placeholder tokens used when pre-processing occurs, there are inclusion directives like pound include, if-def, there are literals that potentially need pre-processing. There are string literals. there are pre-processing operators and punctuators and single non-white space characters that don't lexically match other categories. So at the end of the day, we've got pre-processing tokens. Each comment is replaced by one white space character, and all the new line characters in the source are retained. In stage 4, pre-processing directives, the if-defs, the pound include, the things that begin with the pound sign, are executed and macro invocations are expanded. Each file that's included by an include directive is processed by phases 1 through 4 recursively. And this is done in order and recursively until all the pre-processing directives are removed. So for example, if you pound include a file foo.h, during this phase, the contents of the file foo.h are included in your stream of tokens, and the directive include foo.h is removed because the actual text of foo.h has been substituted in the stream of tokens where that include directive originally occurred. In phase 5, the characters that are character literals and string literals are converted from the source character set to something called the execution character set. And the execution character set is something that could be a multi-byte sequence such as UTF-8. It could be a wide character sequence. It could be some more generalized character set. However, the requirement for the execution character set is that the 96 characters of the basic source character set that I mentioned in phase 1 have to be supported. Also, escape sequences and universal character names in literals and raw and non-raw string literals are expanded and converted to the execution character set. Phase 6 is actually pretty straightforward. In phase 6, any string literals that occur adjacent to each other in the text of the program are concatenated. So you can have two string literals. You could have hello in double quotes, and if immediately after it you have a world also in double quotes, those things will be concatenated. And the last double quotes of hello and the first double quotes of world will be removed. And then you'll have a single string with one set of quotes that says hello world. Now at the end of phase 6, we actually have constructed the translation unit. All the inclusion directives have been performed, all the conditional compilation directives have been performed, and all macros have been expanded. Now, it should be said, at least the standard says, that source code files and translation units and the output of translating a translating unit doesn't need to be stored as files. There is no requirement that there's a one-to-one correspondence between any of these entities and any external representation like a file. The description that the standard provides here, they warn you, is conceptual only and doesn't specify an implementation. In the real world, everybody does this with files. Now in phase 7, each pre-processing token is actually converted into a parser token. And the resulting set of tokens then are syntactically and semantically analyzed, and they're translated as a translation unit. So the output of phase 6 is the translation unit that feeds into phase 7, and phase 7 translates that input as a translation unit. In phase 8, each translation unit is examined to produce a list of required template instantiations, including the ones that are requested by explicit instantiation directives. The definitions of the templates are located, and the required instantiations are performed to create a second form of output called an instantiation unit. So at the end of phase 8, we have something called the translated translation unit, which is typically an object file. And the translated translation unit, the object file, was formed by parsing the translation unit, by creating an instantiation unit, one or more instantiation units, and from all of those things together, building object file output. Phase 9 is what we normally think of it as linking. And in this phase, the external entity references are resolved, translation units, instantiation units, library components that are needed to satisfy all external references. Everything is collected into a single executable program image. All the disparate pieces of object code that have been created along the way are now stitched together by the linker to create an executable. So to summarize, in phases 1 through 6, we do lexical analysis. These are the phases we usually think of as pre-processing, and as I understand it, are typically executed by the preprocessor itself. The output of phase 6 is the translation unit. Phases 7 and 8 perform syntax analysis, semantic analysis, and they do code generation. And taken together, these are the things that we usually think of as being compilation. The output of phase 8 is a translated translation unit, i.e. object code. Phase 9 is the thing that does our image creation. And this is what we think of as linking. And again, the output of linking is an executable image that can run on our destination execution environment. So let's look at our very simple program, the one that I showed a few slides ago again. This is only a few lines of code, and it's very simple. So we have two source code files here, hello CPP and main.cpp, which need to be compiled and linked together in order to form a program. So let's have a little bit of fun. How many lines of code are output at the end of phase 6 into the translation unit? Well, we can figure this out by inspecting the contents of the translation unit, or something at least that's very close to it. With GCC, you can use the -e flag, and what you can do is generate the contents of the translation unit that would have been fed into phase 7. So in this case, here are the commands that I use to create main.i and hello.i, which are the translation units, or something representing the translation units that correspond to hello.cpp and main.cpp. So again, how many lines of code do you think were created? Well, 41,625 for main.i and one fewer for hello.i. And this is using GCC 10.2 on Ubuntu 18.04. So given the way this works and the fact that before heading into syntactic analysis, we are lexically including everything that needs to be processed in order to perform syntactic analysis, you can sort of see why this model of compilation has driven the evolution of our tools, our tool chains, and our ecosystem. And you can begin to sort of feel why there's this bifurcation between header files and source files. Now, it's not enough information to understand that difference, and we'll come back to that later. So now I'd like to talk about declarations, definitions, and the one definition rule. And these three things are probably the most important things to take away from this talk. Declaration and definition have specific meanings, although they typically get conflated. So in order to understand definitions and declarations, we have to understand what an entity is. The standard defines an entity as being one of these things. I'm not going to read the list to you, but you can see there are quite a few. And the way I think about this list of things is these are things that we create. These are things that in some direct way correspond to something in the executable image that is either data or executes. An object, for example, that is directly something that exists in the executable image. We give objects names, right? So any of these things that exist is thought of as being an entity. So let's talk about names. The standard says that a name is the use of an identifier, and that goes on to list several different forms of identifier that denotes or refers to an entity or a program label in the code, and we're not going to mention labels anymore. So every name that denotes an entity must be introduced into the translation unit by a declaration. Conversely, a declaration introduces those names into the translation unit. A declaration can also reintroduce a name into a translation unit. And you see this sometimes. It's easy to do if you've declared a function int of f, and f takes no parameters. You can redeclare that function time over and over, and the compiler doesn't complain because you're reintroducing that name f into the translation unit. Now, a definition is a subset of declaration. It's a declaration that fully defines the entity that's being introduced. A variable is an entity that's introduced by the declaration of an object. And there's this other thing, or of a reference other than a non-static data member. But if you declare an object, you are defining it. You are instantiating an entity. So going back to the idea of declaration, informally, what you're saying to the compiler is, in this translation unit, informally, here's a new name, or here's a name that you've already seen. I'm just bringing it to your attention again. A definition you can think of informally as being a declaration that says, here's a name, and here's everything you need to know about that name in order to use it, to be able to generate code for it. So then the standard goes on to say that every declaration is also a definition unless it declares several things. I'm not going to list all of them, but I think the takeaway here is that if you use C++ for any length of time, you'll begin to develop an intuition for what a declaration and what a definition is. And you'll understand when to provide definitions and when not to provide definitions, when to use declarations and when to use definitions. But at the end of the day, the way I like to think of it is the set of definitions is a subset of the set of declarations. So every definition is a declaration, but not every declaration is a definition. So let's do some Venn diagrams like I used to do when we were in elementary school. So we have a big set of declarations, and we have a subset of definitions. So on the left, I have declared an extern int called A and an extern constant called C. On the right, somewhere in my program, I have to define the extern int A and the extern int const C. And I define by initializing them in some translation unit in the program somewhere. On the left, here I have a declaration of a function declaration that has no definition. And this is very common. We see it all the time in headers, right? If you ever worked in C headers typically consist basically of function declarations, right? And the code is defined in source code files elsewhere. On the right, we see a definition of that same function. Now, this definition of F is also a declaration of F. On the left, I have a declaration of the class foo. Perhaps I'm using it as a forward declaration. And on the right, I have a definition of the class foo. So the definition of class foo provides the compiler with all the information it needs to understand how the class is laid out, how it's represented in memory, and how it can be used by its clients. The declaration of a class doesn't provide any of that information. The one thing you can do with the forward declaration of a data type that's very useful is to use it to form a pointer type. If I wanted to form a pointer to foo, I don't need to know what's in foo to form a pointer to it. I just need to know the name because pointer to foo is a different type than foo. I can also have a using declaration which pulls in a name from some namespace, in this case, capital N. So I can declare it because I'm going to use it somewhere. And on the right, I can define it somewhere. And I have to define it so that it can eventually be used elsewhere. Here on the left, I've declared an enum, a strong enum, whose type is color, and whose representation is an int. I can do this, and I can actually use these in limited circumstances without defining them. On the right, I'm also providing a declaration of color, but in that declaration is also a definition. And here I'm defining the enumerators that are part of that enumeration, red, green, and blue in this case. Moving on, I can define a struct bar, and bar has a member function, compute X. Now, what we see on the left is a declaration. I've defined the struct bar, and I provided enough information here so that it can be used, but I've only declared the member function computex. So somewhere in the program, I have to provide a definition of computex. So perhaps in a source code file somewhere, I would write the definition that you see on the right. Now, some declarations do not have corresponding definitions. In particular, type aliases are a very good example of that. If I create a type alias through a using directive, or I create a type alias by using typedef, in either case, there is no corresponding definition that goes with that declaration. The declaration is sufficient to use by itself. Let's talk about another concept called linkage. Now, C++ allows some declarations of an entity to occur in more than one place in the same program or translation unit or scope. Now, if a name refers to any of these things that I've listed here, that name might have a property called linkage. If a name has linkage, what that means is that name refers to the same entity as when that name was introduced by a declaration in a different scope. So if I introduce a name X in two different scopes, and that name X in those two different scopes refer to the same entity, then those names have linkage. A name can have three different kinds of linkage: external linkage, internal linkage, and no linkage. External linkage occurs when an entity with a name that has external linkage can be referred to by names from other scopes in other translation units, or from other scopes in the same translation unit. Internal linkage occurs when an entity can be referred to by names from scopes only in the same translation unit. And no linkage is the case where an entity that has a name can only be referred to by names in the scope where that entity exists. So think of it as being external linkage means a name can be linked. A name can have linkage at any scope in the program. Internal linkage means that a name can have linkage anywhere inside a translation unit. And no linkage means that a name can only be referred to inside the block where it's declared. Let's look at an example of external linkage. On the left, I've got my header.h, and on the right, I've got my source.h. On the left, I've got my header.h and my source.cpp, and on the right, I've got another source file. So the names that I've highlighted here in yellow represent, they name entities. So F names a function that's defined here. X names an integer that is declared in this spot. The type alias capital I int is an entity that refers to the primitive type int. Below it, in my source.cpp, I define F. In this code on the right, my other source, CPP, I've included my header, which means I have introduced the names F and X into the scope of my other source. So those declarations occur here. And now, having declared X once, I declare it again, and I also define it. Next, I define a function called G, which returns F modulo 3. So the point here is that the names F, X, and int all have external linkage because these names can be used across translation units. They're being used in two different translation units. If we extend the example a little bit more, let's add an unnamed namespace in my other source.cpp. And let's define a variable y. Let's define some struct with a member function called fuzzy, and let's define a type called foobar. I'm going to use those names. I'm going to expand the definition of my function g, and I'm going to use those names in that definition. In this case, y and foobar have internal linkage. They have internal linkage because they're only visible inside this translation unit. my source.cpp on the left has never seen these names. And so far, these names have no linkage in this translation unit. However, the names y, foo, and foobar do have linkage inside this translation unit, the translation unit that's created when pre-processing is done on my other source.cpp. Finally, we have the case of no linkage. Inside my function g, I'm going to create a type def foobar. I'm going to instantiate a variable of type foo called myfoo, and I'm going to create an integer called z. These things, the type def, the type alias foobar, the variable myfoo, and the variable z have no linkage. They are only visible inside the function where they are defined. And these rules, they conform to our common sense. They make sense, but they are formally defined in this way through the concept of linkage. The standard actually has quite a bit to say about linkage, and can't go through it all, but I hope that suffices to give you some flavor of what it means. Let's move on to the one definition rule. There are actually several pages in the standard that define this. I'm going to try and keep it short and succinct and hopefully provide some guidelines that make it meaningful. So in a given translation unit, there can be at most one definition of any of these things that you see. There can be multiple declarations in that translation unit, but there can be only one definition. There can, for example, for a function, there can be, as we saw, multiple declarations of a function, but only one definition. A given program has to contain exactly one definition of, across the program, has to contain exactly one definition of every non-inline variable or function that's used in the program. This conforms to our common sense. Again, multiple declarations are okay, but there can only be one definition. On the other hand, for an inline variable or an inline function, a definition is required in every translation unit that uses that variable or calls that function. Now, back in the day, inline, when it was first introduced in the language, was intended to be a suggested optimization that the programmer made to the compiler. The programmer was saying, hey, I want you to take this bit of code, and I don't want you to actually create a function that gets called with the expensive process of pushing arguments on the stack and returning a value. I just want you to expand the code in line. Well, compilers have gotten very smart about doing this these days, and compilers will inline code in that fashion that you haven't requested to be inline. The compiler will do anything it wants to make sure that your code runs as fast as possible. So inline no longer has its original meaning. What it really means these days, what it has evolved to mean is please allow, or it means multiple definitions of this variable or this function are permitted. So I can have an inline function, I can put it in a header, it can be included in multiple translation units, it can be used in multiple translation units. And this inline variable or inline function is an exception to the rule in that multiple definitions are permitted. Along the way, exactly one definition of a class must occur in any translation unit that uses it in such a way that the class needs to be complete. So that means, by being complete, that means that the compiler sees how to build the class. It sees the full definition of the class so that it knows what member data is in it, what member functions it contains, and can decide how to lay it out, how to represent it, how to generate the object code that go with supporting that class and running its member functions. And so examples here, well, like a constructor or calling a member function. If you need to use some facility of a class, if it's a struct and you need to access its public data members, or it's a class and you need to invoke a member function, or you need to construct that class, the compiler must see the full definition of the class in order to do its job. So let's look at a few quick examples of the one definition rule. So on the left, we have a translation unit 1, and on the right, we have translation unit 2. On the left, I'm declaring a const int externally, and on the right, I'm defining it. That's fine, perfectly allowable. However, if I define the same integer in two different translation units, this is not allowable. This is a violation of the one definition rule. So this is invalid code. Again, assuming both translation units are being linked into the same executable. In translation unit 1, I've got the declaration of function f, and maybe I use it somewhere in translation unit 1. In translation unit 2, I define f, and I can use f in translation unit 2 as well. But the important point here is there is only one definition of the function f in the executable. If I do this, for example, forget to put inline on a function like this that might go in a header file, I have multiply defined symbols, and this is a violation of the one definition rule. And this is the kind of thing that's an ill-formed program with no diagnostic required. The compiler cannot sense that this occurs that this function is defined in two different translation units. Only the linker can sense this and then issue a link error. I can define the class and provide full definitions of a class in two different translation units like this. And the member function, or the constructor foo, I've defined in the class declaration itself, or in the class definition, and so it's implicitly inline. So this is perfectly valid code. This full class definition can be used in translation units like this, and there's no violation of ODR. I can also do this. I can have a member function declaration for foo's constructor in translation unit 1, and in translation unit 2, I can have the full struct definition, and I will define the member function. This is also perfectly valid code because I have not requested the ability to have multiple definitions of foo. It's not inline. And I've provided only one definition of this constructor. However, if I do something like this, where I define the same constructor out of line in two different translation units, that's a violation of ODR. And again, you'll get multiply defined symbol link errors. So ODR is complicated. There are exceptions and low-level details. But I have a couple of simple guidelines that I try to keep in mind when I'm working, and they work for me 99% of the time. And so I'm going to share them with you. First of all, for an inline thing, something that's inline, whether it's a variable or a function, and that thing that's declared inline gets used, make sure that that thing is defined at least once in some translation unit somewhere. If it's used in a translation unit, it must be defined in that translation unit. So make sure that happens. For everything else that gets used, make sure it gets defined exactly once in one translation unit. I'll talk briefly about storage duration and objects. Every object has a storage duration. There are four kinds. There's automatic storage duration, where object storage is allocated at the beginning of an enclosing block and deallocated at the end of the block. This is something that applies to all local objects, objects that are declared inside a function or a member function, except those that are declared thread local or static or extern. Those have different storage duration. But if you think about writing a function f, and inside f you declare string s and you do something with string s has automatic storage duration. There's dynamic storage duration, and this is duration of storage that we as programmers control explicitly. The storage for objects is allocated and deallocated by our code in the program using functions that perform dynamic memory allocation. Objects with this duration, with dynamic storage duration, are created using new expressions and delete expressions. In other words, the new operator or operator new, the delete operator or operator delete. There's static storage duration. This is storage duration that's allocated at the beginning of a program and deallocated at the end of a program. In other words, static storage is allocated for the program before the program execution enters main, and it is cleaned up and deleted after main exits. Now, static storage duration applies to all objects that are declared at namespace scope, including the global namespace. It also applies to any objects that you declare static or extern. So anything at namespace scope, static or extern, is going to be constructed in static duration storage. Importantly, for some object that is declared at namespace scope or static or extern, and which has static storage duration, there can only be one object with a given name in static storage in the program. So you can't have two global variables in the same namespace of the same type named X, or actually even not of the same type named X. Thread storage duration is when object storage is allocated when a thread is created, and it's deallocated when that thread ends. This is storage that applies to objects that are declared thread local, and in this case, every thread has its own instance of an object with this thread duration. In the few minutes I have left, I want to talk briefly about what ABI is. ABI stands for Application Binary Interface, and it's a platform-specific description of how entities, which we define in one translation unit, interact with entities that are defined in another translation unit. For C++, this includes things like name-mangling for functions, name-mangling for non-template types, name-mangling for template instantiations, the size, layout, and alignment of objects of any given type, how the bytes in an object's binary representation are to be interpreted by the program, the calling conventions for passing arguments to functions and receiving objects that are returned from functions, and the calling conventions for making system calls into the operating system. On Linux, GCC and Clang used something called the Itanium ABI. On x86, x64, Microsoft and Visual Studio and Windows uses its own ABI. Let's talk briefly about what name-mangling is. Name-mangling refers to the way in which entities in a translation unit are transformed into symbol names in object code. Now, C++ historically has deliberately maintained binary compatibility with C. This means that C++ object files can use functions and data that are defined in C object files, and with a little bit of work, the other way as well. Now, the C language does not provide overloading or namespaces. So given a C function with this very simple declaration, the corresponding symbol name for that function is basically taking the name of the function and prefixing it with an underscore. It's that simple. This is usual for C. So because there's no overloading or namespaces, there's no need to further refine that name. The function name foobar will be uniquely represented by the symbol name underscore foobar in the object code when the program is linked. And there should only be one set of object code referred to by the symbol name underscore foobar in the entire program across all of the set of object files. So the symbol name here is the same no matter how many parameters or what their types. So reusing names in C can be tricky, right? It's difficult or it's painful. Well, C++ does support overloading. It's one of the most important and interesting features, and it supports namespaces. And this allows us to use short human-readable names in many different scopes or many different contexts. So what we need to do is we need to be able to map the name of a C++ entity into a name that can coexist with the names of C entities. So that means that every overloaded use of a name has to be transformed into a unique symbol name. And the way we do this is we encode extra information about the entity directly into the symbol name. So for example, here's an example that I cribbed from Wikipedia and expanded a little bit. Here I've got a class called article, and it has a public member function called format that returns a string, and it exists in this namespace called Wikipedia. Well, looking through the object files with nm, you can see that this is the name for that entity. This is the symbol name that is associated with the object code that goes with this member function. It's long and ugly and hard to read, but it's a unique symbol name that corresponds to the conventions that C looks for. If I declare another function, I overload the name format, and in this case, it takes a const ref to a string and a 64-bit signed integer as arguments, and also returns a string. And it has the same name format, so I'm reusing the name format. It has a much longer and uglier symbol name. But again, it is sufficient to distinguish it from other C symbol names. So linking is the final stage of compilation, which is performed by the linker. And as I've said a couple times before, it combines object files and libraries to produce the final executable. It does this by examining all the object files to find all the symbols that are in them. It determines the set of all the symbols that are used by the program. It resolves references from internal symbols and external symbols. It assigns final addresses to the symbols that represent functions and variables. It revises code and data to reflect these addresses, object code and data to reflect these addresses. It emits executable code. An important key here for everything to work is that the compiler and the linker have to agree on the ABI, which means they both have to understand data layouts and calling conventions and other things. So both have to understand object code in the same way. Loading and running. Well, you get ready to run your program. The operating system loader validates the executable file. It checks the permissions. It checks the resource requirements, like, do I have enough memory to run this program? It verifies that the file is indeed executable and that the instructions it has are valid. The operating system then loads and runs the image. It does this by copying the executable image into memory. If there's any dynamically linked libraries, there have to be the final resolution of unresolved symbols. This is called relocation and fix-up. Command line parameters given to the program are copied onto the program stack. Registers that are going to be used are initialized. The stack pointer is set to the top of the stack, and other registers are cleared. Control jumps to the start routine, which performs program initialization and calls main with the command line parameters. And at that point, you've got a running program. So I'm just about out of time here, and that's the end of my presentation. Thank you for attending, and I hope you got something out of this talk. I'll answer questions for a couple of minutes. I don't want to run over for too long. Let me just go to Remo here. Okay, so the first question is, can you expand on why we can define classes multiple times? Why doesn't that violate the ODR? So remember, a class definition by itself doesn't actually, if you have a class definition that only declares the member functions in it, or the member functions are declared inline inside the class declaration, what you've said to the compiler is, here is the definition of the class. Here's the name of all the member functions. Here's all the data members the class is going to contain. Here are some member functions that may be declared inline, right? Go ahead and use that information in translation unit A. Well, in translation unit A, if I call those class member functions that are defined inside the class, they are implicitly inline. They're inline functions. And inline functions are allowed to be used in multiple translation units without violating ODR. If you think back to the example that I gave, and let me see if I can find it very quickly. If you think back to this example, here I've got a class definition, but the member function itself, I've defined it out of line. And so it's this definition of this function that's actually violating the ODR, because in this particular instance, it's out of line. In this case, the class is defined, and simply the definition of a class is not enough to trigger an ODR warning. My member function is inline, so I can define it and use it in multiple locations because that's what inline means. This is okay because I've I've defined the class and declared the member function, and in another translation unit, I have redefined the class, effectively redeclaring everything that's in it, and I've defined the member function. And classes are actually called out as one of those exceptions in ODR that say, in the standard that says, classes are allowed to be defined in multiple translation units without violating ODR. I hope that answers your question. Last question, will the slides be shared with participants? Well, yes, they will. I will put them up on my GitHub account. Give me a moment. I will pull up my last slide that has that information. Okay. So I will take this presentation and the presentation I did before this one, and they will be up on GitHub today, by the end of the day. Not going to do it right now. I'm going to take a break. So thank you for coming, everyone. I really appreciate your attending. I hope you got something useful out of this, and I hope to see you all in the hallway. Take care.